This is what is visibly a nova seen in the night sky. Now, here's what's cool. T Corona Borealis has been repeating this every 80 years. We have evidence of this going back centuries. What's the evidence? Every time it explodes, there's a gas layer moving slowly away from the system. We have deep photos from specialized telescopes that reveal these shells of gas, offering a record of all the previous times this has gone nova.
So, why can a star explode again and somehow not die? Imagine looking up one night, seeing a new star flare into view, brighter than anything around it. And then astronomers tell you, relax, we already knew this would happen because it did the same thing 80 years ago and 80 years before that. That sounds wrong at first because we usually think of stellar explosions as one-time events, cosmic final acts. The twist is that in a recurrent nova, the explosion is real and violent, but it only involves a thin layer of gas on the star's surface, not the entire star itself. That detail is what allows the system to reset, reload, and go off again, while leaving behind visible shells of gas that act like a written record of each past eruption. Many stars, like our Sun, do not simply wink out when they die. They leave behind a dense core called a white dwarf. A white dwarf is what remains after a Sun-like star exhausts the nuclear fusion in its core, blows off its outer layers, and collapses under its own gravity until the electrons in its matter are packed as tightly as quantum rules allow. That quantum resistance to further squeezing is called electron degeneracy pressure, and it is what prevents the white dwarf from crushing into something even denser. The important point is that a white dwarf is extremely compact, about the size of Earth but with about half the Sun's mass, so its gravity at the surface is tremendously strong. By itself, a white dwarf just cools and fades, but in a nova system it has a crucial partner, another star. So why does having a partner star change everything? Picture a pair of stars orbiting each other so closely that the outer gas of the normal star is barely held in place by its own gravity. In some configurations, that gas can be pulled towards the white dwarf, sliding downhill in the gravitational field, the same way water flows downhill on Earth, forming a swirling structure called an accretion disk around the white dwarf. As this hydrogen-rich gas piles onto the white dwarf's surface, it builds up a thin shell under incredible pressure and temperature, because the white dwarf's gravity is squeezing it hard. When the conditions cross a critical threshold, nuclear fusion suddenly ignites in that shell in a runaway process, releasing energy explosively. That is the nova. The surprising part is that this thermonuclear blast does not blow the white dwarf apart. Instead, it ejects mostly the accumulated surface layer, flinging that gas outward at speeds of hundreds to a few thousand kilometers per second, fast enough to escape but slow compared with the speed of light. Over decades and centuries, that ejected gas expands into a bubble or shell around the system, thinning out but still present as a large, faint structure perhaps light years across, where a light year is the distance light travels in 1 year. With sensitive telescopes and long exposures, astronomers can directly image these shells, and by measuring how fast the gas is moving, estimate when each shell was launched. In this way, space itself becomes a kind of archive. Each nested shell is a time-stamped page in the system's explosive history. A single eruption might last only weeks to months in our skies, yet its physical aftermath persists for centuries, and we can read it. Imagine peeling back the layers of an onion, except each layer corresponds to an earlier outburst, expanding gently outward long after the flashes have faded from human memory. By taking spectra of the gas, breaking its light into colors, and measuring which wavelengths are absorbed or emitted, astronomers identify the chemical elements in each shell and their speeds along our line of sight. That is how we know these thin bubbles are not random clouds, but material blown off in repeat events from the same system. The counterintuitive insight here is that although light from the flare is brief, the matter it throws into space lets us reconstruct a multi-century story from a snapshot image. So why do some of these systems repeat like a cosmic clock while others explode only once? The recurrence time depends on two main factors: how fast the companion star supplies fresh gas, and how massive the white dwarf is. A more massive white dwarf has stronger gravity, so it can reach the critical pressure and temperature for runaway fusion with a thinner layer of gas, leading to more frequent, smaller eruptions. If gas transfer is rapid, the surface layers pile up quickly, and the system can go nova every few decades. If it is slower, the same process can take thousands of years. This makes a recurrent nova not a mysterious exception, but a natural outcome of very specific masses, distances, and transfer rates in a binary system. Here's the most counterintuitive twist. These recurring explosions may both delay and prepare a far greater catastrophe. There is a theoretical upper limit to how massive a white dwarf can be before its own gravity overwhelms electron degeneracy pressure and it collapses. This is called the Chandrasekhar limit, and it is about 1.5 times the mass of the Sun. Some models predict that, over many cycles, a white dwarf in a recurrent nova might gain more mass than it loses, slowly creeping toward that limit. If it ever approaches that threshold under the right circumstances, the result is no longer a surface flash, but can be a full-scale Type Ia supernova, in which the runaway thermonuclear reactions unbind the entire white dwarf and destroy it, producing a burst visible across a galaxy. Yet, other models suggest the opposite, that each nova throws off enough material to act as a safety valve, preventing the white dwarf from ever becoming massive enough to detonate completely. A recurrent nova, then, is not a star casually breaking the rules. It is a system precisely balanced between gravity, fuel supply, and nuclear physics, allowing it to explode, survive, and repeat. The white dwarf is like a reusable platform. Matter falls on, builds up, ignites, and is blasted away, while the underlying dense core remains intact and ready for the next cycle. The expanding shells preserve a physical memory of those cycles, so that centuries later we can still see evidence of eruptions no human ever recorded. When you hear that a certain spot in the sky is due to flare again, what you are really hearing is that we have decoded this pattern of gravity and fusion well enough to predict with some confidence when the next surface layer will cross that invisible threshold. So the answer to the opening question, how a star can explode repeatedly without dying, is that in a nova, only the borrowed skin burns, while the stellar corpse underneath endures, turning its violent history into a map we can literally see written across space. Like if this was interesting, and hit the subscribe for more.